Bismillahirrahmanirrahim. In this video, we will discuss the effect of controller action on system performance. So first of all, let's look at the proportional control of a system. Here you can see a block diagram in which you have the first order transfer function, first order plant, and here you have the proportional controller, and it's a unity feedback closed loop system. So the closed loop transfer function of this block diagram, let's suppose that is equal to Ts, and that will be equal to C of S divided by R of S. So that's the closed loop transfer function for this system. So what about this error? This error will be equal to this R of S minus this signal, and that is the C of S. So error is equal to R of S minus C of S, and we can write this equation like that, dividing both sides by R of S. So you will get this equation, and then taking it over here, this will become 1 minus C of S over R of S, that is equal to the error with respect to the input. Okay, so now this error signal can be written as 1 minus, taking this one from here, T of S into this R of S. So here you can see this equation. This is the equation to represent your error. You can represent your error either with this equation or with this equation, and you can also represent it like that. Now taking this equation over here, that C of S divided by R of S, that is basically the transfer function, closed loop transfer function, and that is equal to G of S. This is G of S divided by 1 plus G of S for the negative feedback. So taking this from this block diagram, so we can write this transfer function like that, that error with respect to the input is given by this expression. So error signal can be written like that, that error is equal to 1 over 1 plus GS into R of S, where R of S is our input. Okay, now evaluating this error error expression. So taking the value of this G of S in this case is equal to K into K divided by Ts plus 1. So taking that G of S, so we can write down this expression like this. So this is our error equation. And now if we suppose that we are going to apply the unit step input U of t, or in S domain, that will be equal to 1 by S. So evaluating the error for the unit step input, so you will get this equation, right? So what we have done, we have replaced this R of S with 1 of S in this equation. Okay, so for unit step input. Now if we evaluate the steady state error, the steady state error, as we discussed in the previous videos, is equal to limit S applied, limit S approaching to 0 applied over S into E of S. So S into this transfer function, so S and S will be cancelled out, we are left with this part. And if we apply the limit that S is approaching to 0, so this term will become 0, so we are left with that one. So steady state error is equal to 1 by K. So the step response of this system is shown over here. That will be like that, that when you apply the unit step input UFS, that is in terms of S domain is 1 by S, so your system will be giving you this response. And in steady state, when your time is approaching to infinity, you have the constant error, and that is equal to 1 over 1 plus K, and we call it as a offset. Okay, so whenever you have the first order system and the type 0 system, because over here you can see there is no pole at the origin, so it's a type 0 system. For a type 0 system, when we apply the step input, we have the constant error, that is equal to 1 over 1 plus K. Okay, now let's look at the proportional controller that is replaced with the integral controller. Over here you can say the integrator, 1 by S is basically representing the integrator. So integrator, and the integration gain is this K. So now we have introduced this part instead of the proportional controller, simple proportional controller. So now let's write down the closed loop transfer function for this block diagram. So that is given by this equation, that is G of S divided by 1 plus GS into H of S. As it is a unity feedback system, so H of S will be equal to 1, and for this loop the G of S is this one, the product of these two, K divided by S into Ts plus 1, that is G of S. Okay, so now using this expression and calculating the closed loop transfer function, so just replace this g of s and this one over here, and simplifying you will get this one as the closed loop transfer function, that is c of s over r of s. Okay, so now we know that the error signal is given by either by this equation or by this equation. So now using the value of this g of s, we can write down that e error with respect to the input over here is given by this expression. Okay, so now from here I can write down this expression that error in S domain is given by the product of this one multiplied by the input. Okay, and let's suppose that we have the unit step input applied to this system, unit step input. So we will be replacing this R of S with 1 by S. Now calculating the steady state error. So steady state error is calculated with the help of this equation. So applying the limit that at S is approaching to 0, S into E of S, and taking this E of S from here, so S and S will be cancelled out. This S, S into limit S is approaching to 0, S into E of S. So E of S is basically this one. So let's write it over here, 1 over S. So this S and this S will be cancelled out. So now applying the limit over this expression, so you are going to get 0 because of the presence of the S over here, and because this will be multiplied with this one, so you will get ts square plus S. So applying the limit at S is approaching to 0, so this overall term will be 0. So steady state error is 0 when you are going to use the integral controller instead of the proportional controller. So what is the conclusion? That if we use the integral controller, we can eliminate the steady state error, right? So here you can see that when we introduce the proportional controller, that was over here, so if we introduce that one, so there will be a steady state error that will be equal to 1 over 1 plus k, where k is the proportional gain. But if we introduce the integral controller, so the steady state error will become 0. So by the introduction of the integrator for a type 0 system, the steady state error can be reduced. Okay, similarly for higher order system, we have already discussed in the previous video that if we introduce the pole at the 0, what will be the impact at the steady state error of the system response. Okay, now let's look at the response to the disturbance with the proportional controller. A control diagram is shown in front of you. Here you can see a proportional controller, but in this system we have the disturbance coming from some external world. Okay, so this is the input, this is the output, but this is the disturbance that has been added up in this control. So now let's look at that what will be the response because of that disturbance. So as we discussed in the previous lectures, we can, if we have the multiple inputs, we can use the superposition theorem. So for that I am going to assume that in this R is 0, and I am going to find out the transfer function between this disturbance and the output. Okay, so C of S over ds, if you evaluate for this one by considering it is 0, so you will get this transfer function relating C of S with ds. This is C of S, this is the ds, considering this disturbance as an input. Okay, so now we can write down this equation as well, that E of S divided by D of S, that's the error compared with the D of S, right? So that will be equal to R of S minus CS by ds, right? So error is this one. So you have the R of S as the input, you have the C of S as the input, and the error is equal to R of S minus CS, and dividing both sides by D of S, you will get this equation. So as the R of S is 0, so I can write that this is equal to minus C of S over D of S. Okay, so for a unit step input, this D, the input over here, let's suppose the magnitude is TD, and the step input is there, so 1 by S. For unit step input it will be 1 by S, but for level TD disturbance, let's suppose that this is TD, so it will be TD by S. Okay, so from this equation I can write from here, I can write that E of S is equal to minus CFS by DFS into DS. Okay, so taking it from here, so I can write minus 1 over this part, and the DFS is this TDS, that is the disturbance, that is this one. Okay, now if I apply the limit that S is approaching to 0, so the steady state error will be equal to minus TD by KP. So the disturbance has created, and then disturbance will be having this, because of the disturbance we will be having the error in the steady state. So the steady state error is given as TD by KP. So higher the value of this KP, that is the proportional gain over here, so the error because of the disturbance in the steady state will be reduced, because it is in the denominator, right? So as the KP will increase, this is going to increase, the steady state error will be decreasing. Okay, now let's look at the response to the disturbance with the PI controller. Instead of the in this diagram we were having the KP, simple proportional controller. Now we are going to use a PI controller. So PI controller diagram is shown over here, that your error is multiplied with the proportional gain and is fed to the summer block, and the parallel branch have the gain Ki and the integral action, that is indicated by 1 by S over here, and these two are added up over here to give you the net response at this point. So this T of S is basically equal to this one, that Kp plus Ki by S, that is equal to Ts, and if we look at in terms of transfer function relating this one and this one, so Ts by Es, that is equal to the sum of these two parallel branches. These are the two parallel branches. Okay, so now we can write this equation like this, and let's define this Kp over Ki as Ti. So the transfer function of your PI controller can be written like that. In that, this Ti is given by this equation. Okay, so now with this, if I want to look at the disturbance response because of the disturbance, so I will consider this input 0. So considering it equal to 0, if we look at the net transfer function from D to S, so that will be given by this block diagram. Okay, now so finding out the net transfer function, it's a feedback system, so G of S divided by 1 plus the loop gain, that is over here. So simplifying that, we will get this expression, that is Cs over D of S. Okay, so we have this transfer function relating the output with the disturbance input. So now we can find out the error. The error is given by this equation, that R of S minus C of S, that you can see over here. R of S minus C of S, right? So dividing both sides with D of S, and then taking this one equal to 0, so you will be having error with respect to the disturbance given by this equation. Okay, so now this will be equal to negative of this one. Now for unit step input, for the error can be calculated like that, this transfer function multiplied by the D of S, that will be over here. So let's suppose that there is a unit step disturbance. So for unit step disturbance, this is the error equation, and if we calculate the steady state error with the help of this equation, so using this E of S over here, and then this S and this S will be cancelled out. So if we apply the limit, this is 0, this is 0, this is 0, this is 0, so because of that your steady state error is 0. So if we use the PI controller, the steady state error is reduced to 0, right? So what we can conclude over here, if we introduce the integral action in the loop, open loop, and that makes the steady state error minimized, and if the in number of integrators are sufficient, the steady state error will finally become 0. Okay, so but when we introduce this Kp and Ki, the overall order of the system will be the third one, and because of the third order, for certain values of Kp and Ki, the system may become unstable. But your second order system, if all the coefficients of the differential equation defining the second order system are positive, then your second order system is always stable. But if you have the third order system, the positive coefficients along with this Kp and Ki may not guarantee the complete stability. There may be the roots in the right half plane and can make your system unstable. So for certain values of Kp and Ki in the third order system, you can observe the instability in your system. Okay, now let's look at the derivative control action, and first of all let's consider a simple inertia load, that is this one, and we are going to introduce a proportional controller. So the closed loop transfer function for this one is given like that: CFS divided by R of S, that is equal to G of S divided by 1 plus G of S. So simplifying, we will get this expression. So from here I can write down the characteristic equation, that is this one: J square plus Kp, that is equal to 0, and it can be written like that. And we have the two poles in the S plane, and those poles are over the imaginary axis. So if I sketch those poles, so those will be like that: one will be over here, J Kp by this is J, capital J, and one will be over here minus J into Kp by J. So as we have the poles on over the imaginary axis, J omega axis, so our response will be oscillatory, right? So that you can observe where that is the system response when we have only the proportional controller for this inertia load. Now let's introduce the PD controller. In the PD controller, what we have one proportional path and the other one is the derivative part. We have one proportional gain over here and the derivative gain and this is the derivative action. Okay, so these are the parallel branches, these are summed over here, and you get the net response E of S. So input to this controller is E of S, the output of this controller is, let's suppose, C of S. So the transfer function for this PD controller is this one. So now if we take Kp common out, we can write it like this, and let's suppose that Kd over Kp is Td. So the transfer function of your PD controller is given by this expression. Okay, so now let's replace this proportional controller with the PD controller with the inertia load. So your closed loop will look like this. This is your inertia load, and here you have the PD controller. So if you look at the closed loop transfer function for this block diagram, so that is given by this expression. This is the G of S 1 plus G of S, that is the loop gain. Okay, so simplifying this one, we are going to get this expression. And if we look at the response of this equation, so that will be this one. So here you can see if we introduce the derivative control action, so what it is going to do, over here there was no inertia, no damping. Your response was oscillatory, that means there is no damping in your system. So when you use the derivative derivative part in your controller, so that introduces the damping. So because of the damping, now you can see your response is going to become like that, right? So that's the property of the derivative control action, that it introduces the damping in your system, right? So you can adjust the response of your system with the help of the derivative action. Okay, so derivative control action when added to a proportional controller provides a mean of obtaining a controller with high sensitivity. So an advantage of using derivative control action is that it responds to the rate of change of actuating error and can produce a significant correction before the magnitude of the actuating error becomes too large, right? So thus derivative control action anticipates the actuating error, initiates an early corrective action, and tends to increase the stability of your system, right? So the derivative control does not affect the steady state error directly. It adds damping to the system and thus permits the use of the larger values of the gain K, which will result in the improvement in the steady state accuracy, right? So because the derivative control operates on the rate of change of actuating error and not the actuating error itself, so this mode is never used alone. It is used with the proportional action. So it is always used in combination with the proportional or proportional plus integral control action, right? So if I conclude what we have discussed in this video, we have discussed the proportional controller, PI controller, PD controller, that how these controllers helps us to reduce the steady state error of the system response, and we can use them to get the desired response. That's all from this video. Thank you very much.